Hi, as you saw from the opening intro, what we're going to do is examine how many squares a diagonal of a rectangle or a square will pass through for different size rectangle. In other words, for a different number of rows and columns. Let's start with the easiest one, which is just one square, one row and one column. The diagonal, as you can see, passes through the same square. One by one square crossed. Another way of writing 1 is 1 plus 1 minus 1. You'll see why in a little while. What about if we keep one row and have two columns? You can see that two squares are now crossed, and we can write 2 as 1 plus 2 minus 1. Can you see why I am writing it that way? What about a 1 by 4? That means one row, four columns. Four squares are crossed, and I can write that as 1 plus 4 minus 1. Let's look at the 1 by 1 again, but this time for a different reason. We can now go down, in other words, increase the number of rows and keep the number of columns as 1. You can see that we are getting the same results for the number of squares crossed. And there is the 4 by 1. Can you see the connection between the rows and columns and why there is a minus 1 in red? This is what's happening. For a rectangle that has one row and n columns, we've noticed that n squares are crossed. And obviously we can go the other way. If there are n rows and one column, n squares are also crossed. And we can write that as the number of rows added to the number of columns minus 1. For example, 1 plus 1, one row plus one column minus 1. One row plus two columns minus 1 gives us two squares crossed. Or here at the bottom right, 4 rows plus one column minus 1 gives us 4 squares crossed. Let's look at another situation. Here's our 1 by 1 again, our favourite. What if we increase that to a 2 by 2? In other words, the number of rows again is the same as the number of columns. You can see that it passes through two squares because it passes through the center here. And I can write that as 2 plus 2 minus 2, just as before I had here 1 plus 1 minus 1. A larger one, 3 by 3, 3 rows, 3 columns, 3 squares crossed, 3 plus 3 minus 3. So we can generalize. If we have a square, in other words where the number of rows is the same as the number of columns, an n by n, then we know that there are n squares crossed. What about this sort of situation, 1 by 3? As before, we know that 3 squares are crossed. We can write that as 1 plus 3 minus 1. A 2 by 5, 2 rows, 5 columns, 6 squares crossed. 2 plus 5 minus 1 seems to work. And finally, a 4 by 7, 10 squares crossed, 4 plus 7 minus 1. So minus 1 seems to be working in all cases. But it's not always true. What we've shown so far is that if the highest common factor of two numbers is 1, that's when the simple formula that we've had works. And when that's the case, when the highest common factor of the two numbers is 1, the two numbers are said to be relatively prime. For example, 1 and 3 are relatively prime because the biggest number that divides into 1 and 3 at the same time is 1. There it is, 1 and 3, highest common factor is 1. For the second one, 2 and 5, highest common factor is 1. And finally, for 4 and 7, highest common factor is 1. And this is what we can deduce from all that. If we have a rectangle with n rows and m columns, and the two numbers n and m are relatively prime, then we know that the number of squares crossed is obtained by adding the number of rows to the number of columns and then minus 1 at the end. Let's look at another situation again. Here's our 2 by 3. What if I double the number of rows and columns? That will give us a 4 by 6. What do you think will happen now with the number of squares crossed? This is the situation. Let's write down some of the things we notice. We have symmetry. We started with a 2x3, and here's another 2x3, exactly the same. So we have two lots of 2x3. Altogether, there are 8 squares crossed, 4 from each 2x3. Do you notice that 2 and 3, what we started with, are relatively prime? So that means we can use our formula previously where we add the number of rows to the columns and minus 1. And because we have 2 of them, 2 lots of 2x3s, we can multiply the whole thing by 2. And that gives us our answer, expanding out the brackets, of 4 plus 6 minus 2, which comes out to be 8. There's our number of rows, number of columns. Can you see any connection between the 4 and the 6 and the 2? It might be a bit difficult at this stage. That 2 is actually the highest common factor of the number of rows and columns. Think about it. What's the highest common factor of 4 and 6? It is 2. And that is not a coincidence. So what we can deduce is that, in general, if we have a rectangle consisting of n rows and m columns, then the total number of squares crossed is n plus m, the number of rows plus the number of columns, minus the highest common factor. Notice the trivial case that we observed earlier. When the highest common factor is 1, we had a 1 here, didn't we? Whereas in this situation, for this example, we had a 2. So there you have it, an explanation of the number of squares crossed when we have different size rectangles and we look at the diagonal. I hope you found this interesting. Please visit my website for more, and until next time, bye bye.